This is going to be our last lecture on new material for the semester. It's lecture 45, Math 2020. In this last installment, I'm going to talk about how to solve certain elementary differential equations using infinite series. If you want to go to a part of the book where this is covered, it is covered in section 17, chapter 17, section 4, 17.4. Okay, so let's get started. Okay, so this is about series solutions to differential equations. So let's start off with an example that we can actually solve if we wanted to by separating variables, but I want to illustrate the method. So suppose we have a differential equation which is of the form dy dx equals y, and we want to solve this equation. So the idea is we're going to assume the function y has a series solution. So you want y to be the sum of a n x to the power of n goes from 0 to infinity. And now we demand it satisfy the equation. Well, let's first of all take dy dx. dy dx is the sum, n goes from 1 to infinity, and a sub n x to the n minus 1. Now, to say that dy xy dx equals y means that the second series is equal to the first series. So we get the sum, n goes from 1 to infinity, n a sub n x to the n minus 1 must be equal to the sum, n goes from 0 to infinity, a sub n x to the n. So we want to equate the coefficients on both sides. So the coefficients of x to the n, well, on the left, the coefficient of x to the n is n plus 1 a sub n plus 1 on the left, and on the right, the coefficient of x to the n is a sub n. So we get an equation involving a sub n plus 1 and a sub n, and I want to solve for a sub n plus 1. So a sub n plus 1 is a sub n over n plus 1. And this works for n equals 0, 1, 2, etc. Okay, so now let's solve the equation. Well, a sub 0, there's no condition on a sub 0. So a sub 0 is anything, it's any constant. And a sub 1, by the equation we just derived, is a sub 0 over n equals 1. So it's a sub 0 over 2. A sub 2 is given by a sub 1 over, oops, I made a mistake. I take that back. A sub 1 is a sub 0 over 0 plus 1, which is 1. So a sub 1 equals a sub 0. A sub 2 is a sub 1 over 2, which is a sub 0 over 2. A sub 3 is a sub 2 over 3, which is a sub 0 over 2 times 3. Let's keep going. A sub 4 is given by a sub 3 over 4, which is a sub 0 over 2 times 3 times 4. A sub 5 is a sub 4 over 5, which is a sub 0 over 2 times 3 times 4 times 5. In general, we see that a sub n is equal to a sub 0 over n factorial. So we now know all the coefficients of our solution. We know that y must be the sum, n goes from 0 to infinity, of a sub 0 over n factorial times x to the n, where a sub 0 is any constant. We can factor out the a sub 0, and we get it's a sub 0 times the sum, n goes from 0 to infinity of x to the n over n factorial. Well, we know that because we know the power series of e to the x, this is just a sub 0 e to the x. But in general, you're not going to be able to identify the function. You're just going to get a series solution in general. So that's the series solution in this case. Okay, so that was an elementary example. Let's do something, let's do a different kind of example of this kind of thing. So here's another example. Let's say 1 plus x times dy over dx. This is not very, this is pretty sloppy. Dy over dx minus x cubed equals 0. It'll be convenient in this one to solve for dy dx first of all. So dy dx is equal to x cubed over 1 plus x. So in particular, if you wanted to solve this using integration, this by separating variables, you would integrate dy, and that would be the integral of x cubed over 1 plus x dx. And that was one of your extra credit problems in integration way back when, and that was a pretty hard integral to do, if you remember. However, there's another way to do this using the series approach, because x cubed over 1 plus x, we can think of that as x cubed over times 1 over 1 plus x. And we know that that's the series for 1 over 1 plus x is 1 minus x plus x squared minus x cubed plus x to the fourth, etc. So this is assuming the absolute value of x is less than 1. This will work, right? Okay, so now we know that dy dx is this series. Now, what is this series? It's minus 1 to the n, x to the n, but we have to multiply it by x cubed, so it's x to the n plus 3, n goes from 0 to infinity. Okay, so now we know what it is. Now, we could just try to figure this out like I did the last example, or we could just integrate this term by term. So integrate both sides term by term. So the integral, in other words, we're going to get dy is equal, dy dx is that. So y must be the integral of the sum minus n equals 0 to infinity minus 1 to the n x to the power of n plus 3 dx. Well, what is that? That is the sum, n goes from 0 to infinity minus 1 to the n x to the n plus 4 over n plus 4. So in other words, this series solution is given by, oh, and there's a plus c. So this is given by c plus 1/3 x to the fourth minus 1/4 x to the fifth plus 1/5 x to the sixth minus 1/6 x to the seventh, etc. So this is a series solution to this equation. This was actually much easier than actually finding the integral of x cubed over 1 plus x, which took a long time to do. Okay, so that's example 2. Now let's do another example. So my final example of today, and this is the last thing we will cover, is an example of the form y double prime minus y prime equals 0. So there's a second derivative and a first derivative involved. And now we're going to make an initial value problem. Now, if you have two derivatives in a differential equation, there are two initial conditions. The y of 0, we're going to let be 1 in this case, and we'll let y prime of 0 also be 1. So this is an initial value problem when there are two derivatives available. Okay, so now So how do we do this? We do this in the usual way. So we're going to let y be summation a sub n x to the power of n going from 0 to infinity. And then y prime is the sum n goes from 1 to infinity n a sub n x to the n minus 1. And then y double prime is the sum n goes from 2 to infinity n minus 1 times n times x to the n minus 2. Okay, so now we know that y of 0 is 1. So we have that condition to deal with. That implies if we plug in x equals 0 into both sides of the first expression, we get y of 0 is 1. We get 1 equals a sub 0. So let's circle that as a condition. And now to get y prime of 0 equals 1, the second condition that appears, we stick x equal to 0 into the second condition, and we get 1 equals uh, uh, 1 times a sub 1, so a sub 1 equals 1. Okay, so now we have the first two coefficients in the solution. But we need to find all the coefficients, and to do that, we have to stick it into the equation. So to say that y double prime minus y prime equals 0 is the same thing as saying y double prime equals y prime. In other words, the sum n goes from 2 to infinity of n minus 1 times n x to the n minus 2 is equal to the sum n goes from 1 to infinity of n minus 1 times n times a sub n, sorry, is n a sub n x to the n minus 1. So now we have to equate the coefficients on both sides. So the coefficient of x to the n, so the coefficient of x to the n that appears on both sides is this. On the left side, the coefficient of x to the n, well, we have an x to the n minus 2 appearing, so we have to shift it up to two numbers. So we're going to get n plus 1 times n plus 2 a sub n plus 2 is equal to the coefficient of x to the n on the right side, which is n plus 1 a sub n plus 1. And that's what I get so far. So we can divide both sides by n plus 1 times n plus 2 to get a sub n plus 2 is equal to a sub n plus 1 divided by n plus 1 times n plus 2. So the n plus 1's cancel and you're left with n plus 2. Okay, so we've derived an equation relating the coefficients. Let me circle that. Now we can use that to start calculating all the coefficients inductively, if you will, or recursively, if you will, or iteratively, if you will. So what are we going to do? So we're going to set n equal to 0. We get a sub 2 equals so n equals 0 gives me a sub 2 equals a sub 1 over 2. And we know that a sub 1 is 1 from back here, so this is a half. Now we go to a sub 3, so that's taking n equal to 1, so a sub 3 equals a sub 2 over 3, which is equal to 1/2 divided by 3, or 1 over 2 times 3. We can take n equals 2 now to get a sub 4 equals a sub 3 over 4, which is 1 over 2 times 3 times 4, and so on. So you can see that from the pattern that emerges that a sub n is equal to 1 over n factorial, and that's for all n 2 or larger. So what you're going to get is the solution to our equation is given by the expression a0, which is 1, plus a sub 1 times x, which is 1 times x, plus a sub 2, which is 1 over 2 factorial x squared, and so on. So in other words, this is summation 1 over n factorial x to the n, or in other words, since you know it, it's e to the x. And we know that e to the x does satisfy both of these conditions because this zeroth derivative is e to the 0 is 1, and the derivative of e at x equals 0 is also 1, and it's the derivative y double prime is e to the x, and y prime is also e to the x. So the equation is satisfied. This is the solution. Okay, so I think that's it for new topics. We're done. The rest of the term will be review.